recording one here. So welcome back. And again, the plan for tonight is I'm going to give a very brief review about coordination compounds. We're going to dig right into the topic of isomers, which are not exclusive of organic compounds, by the way. Then we'll take a break, and then we'll proceed to study something called crystal field theory that explains why these compounds, when you dissolve them in water, give you these bright, blue and purple and pink colors that we're accustomed to see in many of these solutions. All right. So that is our plan for tonight. Let's go ahead and go to our PowerPoint slideshow. And there we are. So transition metals, of course, we've studied them before in our Chem 1A or equivalent class. And they are the elements that are located here kind of in the middle of the periodic table, beginning on period 4. And in the, I guess the Western world or American style of numbering the groups in the periodic table, the groups of the transition metals are the ones that have a B after them to distinguish them from the ones that have A in them, which are the main group or representative elements, which belong to what we also call the S and the P blocks, according to the valence shell that is filled last in these kinds of elements, all right? So transition metals in particular are important because they either have unfilled d subshells, d orbitals, or they give rise to ions that have unfilled or partially filled d subshells. And as we'll see later on, that plays a major role in the formation of these complex ions. If you were able to watch the video or do your reading in the book, we know that a coordination compound consists of a complex ion and a counter ion. And the complex ion consists of a central metal cation bonded to one or more molecules or ions. And the nature of that bonding is something we'll discuss later when we study that crystal field theory that I mentioned earlier on. So this is the typical formula for a coordination compound. And if we were to look at a structure to represent this compound, it would look perhaps like this with an octahedral type of geometry in it. And this picture kind of like breaks down all the different parts. So starting with the central metal ion, which in this case is cobalt, the complex ion consists of the central metal ion with the 6 molecules that are directly connected to it. When we combine that with a net +3 charge and the 3 chloride counter ions, that whole thing is what we call the coordination compound. Many of these compounds are water soluble because they are ionic and they are very easy to dissolve. And like I said, they give rise to solutions that typically have very bright colors. Or alternatively, you can take the solution, vaporize the water, and recover the crystals, the crystalline solids that are made by these coordination compounds, all right? Now, remember that the molecules or ions that surround the metal, the ones that are directly linked to it, we call them ligands. And the characteristic of a ligand is that it has to have at least one unshared pair of valence electrons. So things like water, ammonia, chloride ions, even carbon monoxide, all of which have lone pairs on one of their atoms, they can serve as ligands. If you think about it, and if you saw the video or read the book, you'll realize that the formation of a complex ion is essentially the result of a Lewis acid-base reaction, where the central metal cation is acting as the electron acceptor, or the Lewis acid, and the ligand is acting as the electron donor, or Lewis base. The atom in the ligand that is bound directly to the metal atom, we call it a donor atom. Notice that, for example, with water, it's the oxygen, and with ammonia, it's the nitrogen atom. Notice that in water and ammonia, none of the hydrogens are donor atoms. They don't have any electrons to contribute to this bonding scheme, right? And then the other thing you should have read was that uh, there are ligands that have different numbers of donor atoms. For example, water, ammonia, the chloride, fluoride, bromide ions, all of these we call them monodentate because they only have one atom in the molecule or ion that is the one that is connecting to the central metal cation. But there are some ligands that have two donor atoms. This is what we call the bidentate ligands. And one of them is ethylene diamine. I'm going to show you a picture of it in a little while. And then we have other ones that have three or more donor atoms. Some chemists will go ahead and call them, tridentate and tetradentate. I simply think, let's just call them polydentate. And one example is EDTA, a compound that is used, for example, to remove lead contaminants. So notice that a ligand may have multiple donor atoms. But in terms of the central metal cation, what we're interested in is how many donor atoms are in direct connection to it. And we call that the coordination number. Notice that coordination number is not the number of ligand molecules, but the number of donor atoms. That means that, for example, if a central metal ion has two bidentate ligands connected to it, it would have a coordination number of 4 because each bidentate ligand contributes 2 donor atoms. Let's look at this example, the bidentate ligand ethylene diamine. You can see that it has one nitrogen here on the left and one on the right, each of which have a extra pair, a lone pair of electrons. And so we call that a bidentate ligand. So let's say, for example, that we make a complex ion with cobalt and 3 molecules of this guy. Well, we're going to end up with something that looks like this on the left. That is a description of it. But because ethylene diamine, which we abbreviate, as you can see here, we abbreviate it as EN. I don't know if you noticed that. We abbreviate it as EN. Because it is a very common ligand, we sometimes represent it in the form of a fan. You can see it on the right. Let me switch us over here briefly to our doc cam so you can see this guy in 3 dimensions. So here is the slide that I was just showing you, right? And this is a representation in the molecule form of the bidentate ligand. Notice the central cation in there, and then the fan shapes, which represent those molecules of ethylene diamine. And the green bars in this case represent what we're going to call the coordinate bonds. These are the connections between the donor atoms and the central atom, all right? So if we were in a lab, you would have a kit of these structures that you could play with. So for now, just dream about it, all right? Okay, let's move again to our presentation here. Let's go back to our PowerPoint. Here is another interesting ligand. It's a polydentate ligand, which is called EDTA, which actually means ethylene diamine tetra acetate, if I remember correctly. So it is a compound that is used to form complex ion with lead 2 ions. You can see it here, and you can see how one molecule is capable of essentially providing all by itself 6 donor atoms. I'm not going to call it hexadentate. It's actually polydentate. And you can see on the right side a structural model of it. But in a way, looking at the one on the left, if you use a little bit of your imagination, doesn't it look like it's like a claw kind of grabbing that lead ion? And because of that, the word claw gives rise to calling these bidentate and polydentate ligands sometimes chelating agents. So to chelate means to kind of like grasp like in a claw, right? So these are very important compounds in terms of removing things like, mercury or lead or other metallic contaminants. All right. Now, structure coordination compounds. As you saw perhaps in the video or in the book, you realize that we have quite a menu of possible structures. You have linear, complex ions, tetrahedral shapes, square planar shapes, and of course, octahedrals, which are the ones we're going to study the most here because they're very interesting in the capability that period 4 transition metals are capable of forming these complexes. Now, uh, depending on the coordination number, you can try to predict what the shape of the complex ion is going to be. So for a coordination number of 2, you're going to get a linear structure. Now, sometimes you can't predict. For example, a coordination number of 4, in other words, 4 donor atoms around the central metal cation, as you can see there on the top, you could have a tetrahedral or a square planar shape. You can't really predict it all the time. And as we'll see later, there are many factors that influence the ability of a metal cation to form one or the other type of structure. And for a coordination number of 6, what we have here is we have a octahedral type of shape. All right. Cool. So can you predict what the structure is going to be? Well, in the case of coordination numbers 2 or 6, yes, you can pretty much predict the structure. In the case of coordination number 4, you can't. And by the way, as you saw, I think in your video or in your book, I forget where, you can have other shapes. I mean, there are more complex shapes that you can achieve with, heptahedron and, sort of like different kinds of other shapes. So don't worry about that. We're only going to focus on these 4 that we have here, all right? Now, what we're going to focus on for the next few minutes is on the ability of these compounds to form isomers. And what you have here is a flow chart that shows you the different kinds of isomers. Remember, an isomer, we learned about this in OCHEM. These are compounds that have the same formula but different structures. And just like with organic compounds, with coordination compounds, you can have structural isomers or you can have stereoisomers. So let's look at structural isomers first. These are the ones that are same formula, but the atoms have different connectivities. There are 2 possibilities here. The first one is what we call a coordination isomer. And this is one where the ligand and the counter ion exchange places. So let me come back here to our doc cam here for a moment. And let's look at that same slide that you had in there. And once more, I'm hoping that our connection here holds up, right? All right, I'm trying to get this guy to kind of like catch here. Okay, here we go. There we go. Try to get this a little bigger. Oops. Come on, get a little bigger for us here. Come on. Help us out. Oh, gosh. Okay, let me show you an example of what I mean by a coordination isomer. Let's consider 2 compounds. Both of them are going to have cobalt ions, and then they're going to have, this one's going to have NH3 5Br, and a chloride ion on the outside. And the other one we're going to show you here is, oops, sorry. Same thing, cobalt with 5 ammonias Notice that the difference between these two is simply that inside the complex ion, which is indicated by the brackets, right? Inside the complex ion, in the top compound, you have a bromide ion as a ligand and a chloride ion as a counter ion. In the bottom one, we have, again, we're having problems with the connection here. Sorry, it's kind of lagging a little bit here. In the bottom one, we have the chloride ion, right, as a ligand. And the bromide ion as a counter ion. So that is what we call a coordination isomer. Simply means that in one isomer, the one of the ligands is exchanged into a counter ion in the other isomer. All right, so that's an example over there. Now let me show you another type of structural isomer. We call them linkage isomers. And these are very interesting. And for that, I'm going to go to the next slide here. Whoops, what happened here? Whoa. I don't know what happened here. Sorry about that. Quickly here, let me go back. I accidentally hit the wrong thing here. So this is an example of what we call a linkage isomer. Notice that these are structural isomers where the ligands are attached to the central cation through different ends. So basically, this is a ligand that has more than one possible donor atom. It only uses one at the time that it forms the complex ion, but it could use the other atom in the structure there. So for example, in this case, we have NO2, nitrogen dioxide. Notice that in the compound on the left, it is connected through the nitrogen atom on the bottom of the complex ion. But in the compound on the right, it is connected through the one of the oxygen atoms in there. Notice in the bottom, and I don't know if the colors will translate well into your screens, but notice that the one on the left has kind of like a yellow color, whereas the one on the right has a kind of like a more dark orange to reddish color. All right. And notice in the names there that you have different names for these compounds. All right. As a matter of fact, here is a table that has some of these compounds and their ability to undergo linkage isomerization. So for example, that nitrite ion, the NO negative, sorry, it's not nitrogen dioxide, it's actually the nitrite ion. Notice that it could connect to the metal cation through the nitrogen atom or to the oxygen atom. Similarly, the other three compounds that are here, or ions actually, they can all do the same thing. You might recognize that one on the bottom right, SCN, the thiocyanate. Remember that we saw this guy forming complexes with iron 3 ions to give us a bright red color solution that we use both in identifying iron ions in solution, but also when we study equilibrium constants. Okay, so let's talk about the other category. This is what we call stereoisomers. Remember that we studied this in our organic chemistry. We said that a stereoisomer, these are compounds that are made up of the same types and numbers of atoms. They're bonded together in the same sequence. In other words, the atom-to-atom connections are the same, but they have different spatial arrangements. And just like with alkenes, what you have here is the possibility of forming geometric isomers. These are stereoisomers that essentially cannot be interconverted without breaking a chemical bond. So if you look at this compound on the left, and you look at the compound on the right, notice that we've called the one on the left the cis isomer, and the one on the right the trans isomer. All right? So what is the difference between them? Well, look essentially at the angle between the ligands that are of the same kind. Notice, for example, that in the cis complex, for example, the ammonia molecules are at right angles to each other, and so are the chloride ions in here. But in the trans one, what you have is you have, like 180-degree angles in here. And that is what distinguishes a cis from a trans isomer. In the cis isomer, the ligands in question are going to be at 90-degree angles from each other. In the trans isomer, they're going to be at 180 degrees from each other. All right. Now, this one's a little easy to see, but what about a compound that has a complex ion that has an octahedral geometry? So we're going to look at this one here on the left, and then look at its isomer here on the right. Notice that if you focus simply on those ligands that are on the plane, and again, there are different ways of kind of like showing or sketching the structures of these things to try to kind of simulate three-dimensional space. In these pictures here, what they do is they draw a parallelogram to kind of like give us a sense, okay, that's a plane that extends from like our point of view into the page and behind the page or screen. And so those four ligands, the two chlorides and the two ammonias that are sitting on that, beige colored parallelogram, they are meant to be seen as if we're looking at them from our own angle, and the ones that look like in the bottom, the Cl and NH3, are kind of like pointing towards us, and the other two are pointing away from us. Again, notice the difference between them. If we look specifically at just the chlorides, again, we can see the 90-degree angle here between them, right? In this structure here, whereas in this one, we have a 180-degree angle. You might think that this is not a big deal, but actually, these compounds form, these complex ions form compounds that have different properties. You can see here on the right side that a compound that has the cis isomer has a pink color, and the one that has a trans isomer has a kind of like a dark green color, although maybe on your side of the screen it doesn't show as well. So let's do a little see if one of the challenges with these kinds of things, which you probably experienced back in Chem 1A when you were studying the geometries of different kinds of molecules, if you probably remember that, is trying to visualize things that are drawn on a flat screen or page and kind of like extend that into three-dimensional space. So here are two other structures, and the question is, are these structures different isomers, or are they the same as the ones that we have above? Okay, I'm gonna give you a little bit of a time to process that, to exercise a little bit of your right brain capabilities, perceiving space, and think about it. Are these two different isomers, or are they the same as the ones above, but just from a different perspective? All right, let's do this. Let's go back to our fabulous whiteboard here. So let's look at the one here that is on the left. Okay, let's look at this one first. And I have a model here for it. All right, here it is. So let's say that let me zoom out a little bit here. Okay, there you go. Let's say that the red colored figures are the chlorides and the blue ones are the ammonias. So I'm going to hold it here and I'm going to look at it the same way that you'd be looking at it if you had it in real life. Let me turn a little bit. Oh, there you go. That looks more like it, right? See it there? And of course, I'm kind of covering one of the ammonias here. So the question is this a different isomer? Well, no, notice that if I were to turn this a little bit, let's say, for example, I were to spin it this way and then that way, notice that I end up with the same structure that I have up here, right? See it there? The one on the top left, that is the same structure. So all this structure here is a different angle, a different view of the same molecule, all right? Or the same complex ion, let's say. Now let's look at the one on the right. If we look at the one on the right now, here it is. Notice that in this case, I'm going to hold the ammonia that's kind of pointing at us. And you can see where the chloride ions are kind of like one is above the plane, one is below. And the question is that different from the one that we have up here? Well, actually, if I just spin around this axis here, gonna give it a little spin like that. Notice that now I end up with the same structure that I had up here on the top right. See that? Same structure. So all this thing on the bottom was the same trans isomer, just looking at it from a different perspective. So the moral of the story is, like what we said before, that what is important here is the angle between these things. Okay, that's what is important. In the cis isomer, you have a 90-degree angle between the ligands or donor atoms. And in the trans one, you have a 180-degree. As long as you have that, you know that you have either a cis or a trans isomer. Okay, cool. All right, let's go back to our PowerPoint. And let's continue. Now, let me show you something in case you forgot, but I teach students this little other trick in Chem 1A, and that is if you don't want to be drawing all these like parallelograms and planes and stuff, mainly people like me who have very poor drawing skills, here's another way of doing it. You can use a straight line to indicate a bond that is on the same plane as the paper or screen, a hatch wedge to represent a bond that is going into the patient screen, kind of like away from us, or a solid wedge to represent a bond that's coming out of the page or screen, kind of towards us. So for example, you can see here where we're representing a trans and a cis isomer. Notice the dark solid wedges represent ligands that are kind of pointing at us, coming out towards us. The hatch wedges represent ligands that are kind of like going away from us. And the straight lines represent the ones that are on the same plane as the screen or page in your case. If I'll give you a few seconds for me to write this because I don't think this is in your PowerPoint notes. Let me give you a few seconds to write that before we go to the next type of stereoisomer. You'll notice that in order to get a cis or a trans isomer, what you need to have is you need to have two ligands that are the same, and then the other ones have to be the same also. So if you have a, an octahedral complex like this one, a coordination number of 6, the idea is that 2 of the donor atoms must be the same and the other 4 must also be the same. Otherwise, you're going to have a different kind of isomer. And that's what I'm going to show you in the next one. This is what's called a FAC-MER isomerism. In this case, what you're going to have is you have sets of 3, not 2 identical ligands in an octahedral complex. And the idea is, are they on the same face or are they forming an arc around the central metal cation? Notice in this complex here, you have cobalt as your central cation, and then you have 3 ammonia molecules and 3 chloride ions. Notice the one on the left, the chloride ions are all on one face, in other words, one triangular face of the octahedron. But in the one on the right, they are kind of like running an arc around the central metal cation. So the one on the left we'll call a FAC isomer. The one on the right we call a MER isomer. Notice the notation there, MA3B3. That is kind of like one of the ways that you can use to represent these things So you can basically say this is, it's going to be M will be the metal ion, and then A and B would be the two ligands, and then you can have, let's say, M, small m of this and n of that, and you can represent them this way. This is similar to what we did in the geometry of molecules in Chem 1A with the, I don't know if you guys remember that, the AX, kind of like representation, or AXE, right, or ABE representation between bond atoms and lone pairs, right? Okay, let's wrap up our study of isomers by looking at a very interesting phenomenon that also exists in organic compounds, but I didn't cover them because I felt like I wanted to save it for here, and also in this for the in the interest of time to do it here. Our hands have a property that is called chirality. Actually means handedness. And that is that our hands are pretty much mirror images of each other, but you can't superimpose them. So, for example, if you have a left-handed glove, you cannot perfectly place it on your right hand because either your thumb or the rest of the fingers are not going to be able to fit at the same time. Or if you try to do it, the palm of the glove is going to be facing in the wrong direction. It's going to be facing towards the back of your hand. This phenomenon of structures that are not superimposable on their mirror image has a word. These are called optical isomers. So these are compounds or structures that are mirror images of each other, but you cannot superimpose them. All right. So let's do this. I'm going to show you some structures here. So this is one structure, and let's pretend the bar there in the middle, the vertical bar, is a mirror. And so what I'm looking at is two structures that are mirror images of each other. So let me give you a chance to kind of think about that a little bit. All right. This would be a cis isomer of this compound. Notice that the chloride ions are at 90 degrees to each other. So this is the cis isomer. And it turns out, for reasons we're going to see in a moment, that these two are optical isomers. In other words, this has a chiral arrangement. Let's look at the one on the right here. This is the trans isomer. Notice that the chloride ions are at 180 degrees from each other. These two mirror images are not optical isomers. They are achiral. I know. I think right now, from your perspective, you're going like, what on earth? How do I know that? Well, let me help you a little bit. Let's go to our trustworthy, hopefully still connected whiteboard here. And I'm going to show you how this works, all right? Now, I'm going to show it to you with structures, but there's a video that I'm posting on Canvas that you can look at where a professor walks you through the exercise of doing these manipulations with actual, what am I going to say, like two-dimensional pictures, all right? So let me take us to our, oh, you know what? I don't think our thing is working anymore. We may have lost our connection here. Okay, there it is. Let me pull out a little bit from here. Oops. Okay, so I don't know if you can see that, but you have your slides. I don't know if you can. If you have your notes, you can see this slide. So let's look at the image on the right. This is the cis isomer. All right. So what I'm going to do is I'm going to bring in that structure over here. This is our guy. So I'm going to look at the one on the left. I'm going to. We're losing it. We are losing it. Oh no. Okay, there we go. So this is the structure on the left here at the top, here on the trans isomer. You guys can see it there, right? See the two chlorides are at 180 degrees from each other, all right? I'm gonna bring it over here, down here, and I'm gonna put in front of it its mirror image. So if I were to take these guys and approach them on a mirror, let me kind of zoom out. That's as far as it goes, okay? So here they are. Here's my mirror image of that same guy, right? You can see where the chlorides are kind of like the ones in the middle are kind of facing each other and the other ones are kind of facing away. Notice that I can take this structure here that I just made and I can just basically spin it around. And essentially what will happen is that I will get an overlap between the two of them. Well, it's hard for me physically to do it here, but you can see where you can actually match, each chloride to another chloride, and the spans, the wings of the ethylene diamine, you can see how they can overlap each other. In other words, the mirror image of the trans isomer is superimposable on itself. Therefore, these are not optical isomers. Now, let's look at the other guy. Let's look at the cis version of this, okay? Here is one of them. Let's see this. Let me do it the same way that it's in your picture over here on the top. There you go. So that is one of the cis isomers. Let me turn it a little bit so it looks a little more like that. Okay, there you go. Now it looks a little more like that. Now I'm going to bring in the mirror image of it. Be careful because when you draw the mirror image, they have to be exactly, represented. So here we go. There is the mirror image of this guy, right? Now what I'm going to try to do is, if the internet holds up here, I'm going to try to bend this guy around and match these guys. So let's try matching the red items here, the chlorides. All right, I'm going to come in here. I'm going to try to match those two. And you can see where I can get them to match with each other. But notice the fans of the ethylene diamines. They are at 90-degree angles from each other. They don't overlap. If I keep trying this, and I'm not going to try it because I can see that our connection's a little weak here, but the point is that these two structures represent mirror images of each other that you cannot superimpose on each other. And that is what we call an optical isomer. All right, that's what we call an optical isomer. As I said, in our Canvas page, I have I think a link. I think it's a YouTube video or something where there's a guy kind of like walking through doing all these stuff without the three-dimensional model, just doing it on a piece of paper or board. And you can follow that in case you're interested in how you can process it in your brain to try to visualize what is drawn on a flat screen or paper into a three-dimensional picture. What is interesting here is, how do we know that these things are optical isomers? If we didn't know the structures of these things, how would we know? Well, it's actually a very interesting phenomenon, and it says that chiral molecules, in other words, structures that are non-superimposable mirror images of each other, are optically active. What that means is that they rotate the plane of polarized light. Let me show you a sketch of something called a polarimeter. And like I said, this is just a sketch, all right? Let's say that I have a light source. And what I'm going to do is, the light coming from this light source, you have light waves that are oscillating in all kinds of angles and directions. So a polarizer or polarized filter, what it does is, the equivalent of a grid, essentially it blocks off all of the light except the one that is oscillating in a particular direction. And let's say we're going to call this the 6 to 12 o'clock, let's say the 12 to 6 o'clock direction over here. I'm just going to say for the sake, oops, sorry, I didn't mean to do that. Oops. Let's say for the sake of illustration that we're simply going to use that one there. Oops. All right, that's oscillating, vertically. Let's say between 12 and 6 o'clock. Now, in this tube, I'm going to make that light pass through a tube that has an optically active substance in solution. And what's going to happen is, for reasons that you'll have to study probably in a more advanced course, it causes the light to bend, to essentially rotate. So when it comes out, it is coming out at a different angle of oscillation. And you have a detector here at the end that is going to show us what is the angle at which the light is being rotated. You'll probably see it over here. So any substance, this is very interesting, any substance that has this property of being optically active, in other words, it's a molecule that represents the non-superimposable mirror image of another molecule, will create this phenomenon of rotating polarized light, the plane in which it rotates. So if you have two compounds that have the same magnitude of rotation but opposite sign of rotation, we're going to call these enantiomers. Guys, that's about as far as I can take it, because I think without going into very deep stuff, I don't want to get you guys all mixed up in the wrong things. Just realize that there are many substances in nature, particularly organic compounds, as well as these complex ions that we're talking about, that have this property. As a matter of fact, many substances, for example, glucose, amino acids that are used to make proteins, some of the substances that make, fats and oils, some of these things, they actually have this property, but they actually have more than one chiral center. In other words, they have more than one portion of the molecule where there is this phenomenon of chirality. And so you can generate multiple types of optical isomers with varying rotation angles. So when we talk about enantiomers, it's a very specific definition. So these are going to be two substances, two structures that are exact mirror images of each other, but you cannot superimpose them. And the result is that in a solution of it, you're going to generate a rotation of the plane of polarized light in one direction or the other, same magnitude, just the opposite sign. One will be, let's say, plus 20, the one will be minus 20, or whatever. Now, remember that I told you about the cis and trans isomers having very distinct properties. The reality is that for optical isomers, this is the only distinction between them on a physical level. They behave the same. They have the same melting points, same boiling points. I mean, their physical properties are all the same, except for this one property of how they rotate the plane of polarized light. Now, when it becomes interesting is when you get into their chemistry, because many enzymes, in other words, the catalysts that are used for many of the metabolic chemical reactions, many enzymes themselves are also optically active. In other words, they will recognize one optical isomer, but not the other one. And that is very interesting. So for example, glucose, all of the enzymes that manage the processes of metabolism in our, in our biochemistry, the enzymes that work with glucose can only handle a version of glucose called D-glucose, and the other one, L-glucose, is not used for any of these metabolic operations because the enzymes involved are stereospecific. They recognize only that particular optical isomer. Okay, so we're gonna take a little break here. Let's go back here to my thing. And again, I'm hoping you guys are not having connection problems. But we're gonna take a break. I went a little longer than I was hoping to, but we'll still take. Let's make it a little short. Let's take a 10-minute break. That's fine. We'll take a 10-minute break, and we'll come back. Let me know if you have any questions before we step away.